Welcome back, guys. This is Ashwin here. In this video we are going to see how to do time series forecasting using ARIMA. And SARIMAX is the name of the module we are going to use, and for this tutorial purpose we are going to use air passenger dataset, which is a traditional dataset for time series forecasting. So here we are going to learn all the fundamentals, like how to choose the parameters for the ARIMA and how to do forecasting for any dataset. So let's dive into the video. First we have to import all the necessary modules. So let's import all the modules. Import pandas as PD, import numpy as np, import stats models as sm, because some of the functions we are going to use are from here, and from stats models.tsa.seasonal, import seasonal decompose, and import matplotlib.pyplot as plot, and finally to remove the warnings, so we'll just import warnings dot filter warnings. We'll just ignore all the warnings. Let's run this. Yeah, this is the first warning you usually get. If you run it again, it will remove those warnings. Let's load the dataset. Here we are going to use air passengers dataset. I will add the link in the description for downloading that dataset. You can also find it in my GitHub repo. Read CSV and airpassengers.csv, df.head. You can see there is month and number of passengers. So I'm going to set this month as the index of the data frame, so it's easy for doing visualization. So df.set index of month and in place equals true. If you don't do in place, means you just have to say df equals df.set index. Let's run this. Now you can see, so this has become the index and this is our variable. Now let's do some preliminary analysis. We will jump into the EDA part, exploratory data analysis. Let's create some code cells so it's easy for us. Now we have to plot the data first to see how the representation of data is. So plot.figure, how to set the figure size. You can change the size whichever suits better for you. I'm going with 20 cross 5. Plot df of index, which is the x-axis, and df of hash passengers, which is on the y-axis, passengers, and label is just nothing but number of passengers. I'm just using the same representation everywhere, passengers. And let's also have the labels. X label will be date and Y label will be number of passengers. Let's copy and paste this. And plot.title, number of passengers over time. And plot.legend, I don't think it's needed, as it's very straightforward. Plot.grid, we'll set it as true, so to have like a lines, and it will be easy for us to do the analysis and separate the data along with the x-axis. X-axis is for like rotate the x label in a 90-degree, because it will overlap with each other if you don't do that. Now let's show the graph. Now you can clearly see it, the x-axis, it has all the dates. If you don't do this, let's just comment this one. This is how the plot will look like. So we just have to add the necessary parameters whenever the situation comes up, and you can see there is a clear increasing trend. So we have to remove the trend in order to do the analysis. We will explore more in detail in the upcoming steps. And you can see there is a seasonality as well, that is also we will again explore. And over the period of time, the data values is keep on increasing. As you can see the graph, from here it just gone up to here. So we have to use the corresponding model for this, for using this seasonal decompose. I'm going to use multiplicative. If you have this increasing or decreasing order, or if you have just the same range of values over the period of time, means you can use additive. So let's use the seasonal decompose and plot the trend, seasonality, and the residuals in this graph. So this will help us understand each of the parameter separately with visualization. Perform seasonal decomposition. We already imported seasonal decompose, and in this case we will also use Seaborn. So import Seaborn as SNS. So I'll just say result equals seasonal decompose of df of the passengers, and as I said, I am going to use multiplicative model. Multiplicative, and the period will be 12, because you can see from starting to the ending until this one, you can have a same pattern repeating over time. Even if you say this is the lower point and this is the next lower point, it's starting at 11 and it's again ending at 11. So that's why I'm having a seasonal of 12. So each year we have a seasonality. After this, let's get the results, and each one have like different variables inside it. Now let's run this, and let's plot the graph. Plot the components in the graph, and SNS dot set style will be white grid. So here also we will just set the plot dot figure, fig size 18 cross 14. Again, you can change if you want to. First we will display the trend component. Plot dot subplot 411. SNS dot line plot of data equals result dot trend. Plot dot title, which is trend, and plot dot xticks, which is rotation rotation equals 90. So like this, we have to display another 3 more components. Let's just copy and paste this and replace the necessary variables alone. Here we will display the seasonal component. This will be 412 and seasonal. This is also seasonal. Rest remains the same. Then residuals 413 resid and residuals. Okay, now the original time series, original data, which is not a component, and 414. This will be df of passengers. And I will call it as original data. Okay, now plot dot tight layout and plot dot show. Let's run this. So this is still running, and you can see the different data here. Let's just minimize the graph, at least on the height level, so we can see it in like a single page, at least the main components. So let's observe the trend. So the trend is keep on increasing over the period of time. So we have an increasing trend. We do have to remove that to do further analysis. And as I mentioned before, there is a clear seasonality of 12 months. So the seasonal period will be 12 months, which we will use it later for the parameters. And if you ignore these two, means these are the other residuals that is present in the data. And this is the original time series. So this is how you can do the initial analysis for any time series. So using these two components, you can clearly see the trend and the seasonality and build up further analysis for the data. Okay, after this, let's just define the seasonal period. Seasonal period is 12, which we just found now. Now to do further analysis, we have to remove the trend. So for this, we have to do some differencing. There is different types of differencing that you can apply. For now, we will just use pandas inbuilt function diff to do the differencing part. And to determine how many differencing we have to use add fuller module from stats models dot tsa dot stat tools. Okay, import add fuller. Now here also result add fuller of pass the passenger data values, passengers, and auto lag. Here we have like AIC and BIC. We will use AIC here. So the full form of add fuller is augmented. I'll just have a commented section, augmented decay fuller test, and AIC means ACF information criterion. We also have Bayesian information criterion. For now I am going to use this. Let's print it. It will also return like multiple variables. We are just going to see only the important ones. Here you can see it. It's not like displaying the keys. We have to like displaying the keys as well. So this is the ADF statistic and this is the p-value. So for now we will just display these two alone. If you want to do some further analysis on the rest of the values, you can also do that. As this is a beginner tutorial, I'm going to stick with these two. Let's print this in a proper way. Print ADF statistic result of 0 and print p-value result of 1. Sorry, this is print. You can see the p-value is 0.99. This means the time series is not stationary. You have to make the p-value to 0.05, like less than 0.05, to make the time series stationary. So once the time series become stationary, which is like after removing this trend values, we can do further analysis to find the parameters for the ARIMA model. Now we have to change this. Let's use the test again. Here we can remove this. In this case, I am going to do one differencing. Diff dot dropna. Now you can see after doing first order differencing, you can see the p-value becomes close to 0.05. You can also do further differencing. I will just say first order differencing. And if you do the differencing again, sometimes you have to do 2 times differencing in order to get the p-value like this, and this will be second order differencing. Now you can see it just gone very less than 0.05, so we can just stop at first order differencing here. You can also plot it in a graph to see how the time series is getting changed after doing the differencing. Let's plot the values. Plot the differencing values. Now figure, I'm going to plot like 3 axes. Axis 1, axis 2, axis 3, and plot dot subplot of 3. X1 dot plot, plot df x1 dot set title original time series. So this is the original data without doing any differencing, and we can remove the x-axis for this. So axis 1 dot axis dot x-axis dot set. There is a parameter set visible. I will set it to false, or else we will have so many overlapping date in the plot. So this is for the first, and let's do it for the second. Have to do the same, but axis will be 2, and we have to do the one first order differencing. So diff, if you do differencing, you will get some null values as well. So that's why we are using dropna. I think for the plot we don't need to use that. In this case we need to use, I'll just show it here. Diff, you can see in the initial case it is having like null values. If you do additional differencing, it will have like 2 null values. We have to like drop it if you want to use this without any errors. And first order differencing, and axis 2, Let's do the same for second order differencing, and here we have to do the differencing again. 3 3. Now finally we will plot it. Plot dot show x-axis. Okay, visible, made a mistake. Okay, now it is clear. Now you can see there was a increasing trend. After doing the first order differencing, the trend is completely removed. We just have the remaining values. And if you do the second order differencing, I think the noise becomes so much increasing. So that's why I mentioned we can just stop at first order differencing. So we can see the data or the time series becomes stationary after first order differencing. Okay, so we will use the first order differencing. So whenever we are using, we can just use this directly. Okay, now differencing. So this is also like one parameter for ARIMA. Let's also define here, define parameters for ARIMA. So this is the crucial step, I would say. First, we already found the differencing, which is 1. So this is one variable, the differencing part. Order of differencing. In ARIMA, this is defined as I. And we have p value and q value. This we are going to find out. For now, I will just have it as 0. And this will be MA. And this will be AR. So the full form is moving average, and this will be autoregressive. Okay. So let's define these after plotting the additional graphs to define the parameters. So for this, we are going to plot ACF and PACF plots. So I think for this we have to change this import stats model dot API. So this one change you have to do, and then let's plot it. So fig comma axis equals plot dot subplots of 2 1, which is 2 rows and 1 column. Fig size is 12,8, and sm dot graphics dot tsa dot plot ACF df of diff dot dropna. As I said, we just have to do the first order differencing. Here we are just specifying the lags, how many lags we need to explore, and axis equals axis of 0, and we have to do the same one more time, but in this case we are going to plot PACF and plot dot show. Run this. Okay, I think I made an error. Okay, now this is better. Let's decrease the value here to 10. I just wanted to see it okay, now this is very clear for us. Okay, first let's define the basics. These are ACF and PACF plot, which is autocorrelation and partial autocorrelation. First, let's see the partial autocorrelation. Here, you can see some kind of like lollipop uh, points here. We can just have it as like data points. We always ignore the point at 0, and after that you just have to count how many data points are outside this confidence interval. So this is the shaded region, which is the confidence interval. We just have to see how many data points are out of the confidence interval. So here 1, 2, this is, you can also set it as 3, but it's also inside the confidence interval, so I'm going to say p value is 2 because 2 of them is outside. So p is 2. So this is from PACF, and D we already know, which is the differencing, first order difference, which we already done to get this data, and Q value. For Q we have to do the same. Here you can see only one data point is outside of the confidence interval, so we will define it as 1. So this will be ACF. So this is how you can find the values for ARIMA. Other than this, we can also need to find seasonal ARIMA parameters, which is capital P, D, Q. So first let's use these parameters and build a forecasting model and observe the results. Based on the results, we will find seasonal parameters as well. So now that we got the parameters, let's run this. Let's define the ARIMA model. Define the ARIMA model. So from stats model, TSA statspace dot SARIMAX, import SARIMAX. Previously we can just directly use the ARIMA with the same parameters, but ARIMA is depreciated and this is the ongoing development module, so that's why we are going to use this. And let's define the module SARIMAX of pass the data df of passengers and order, which is the order we just found, P, D, Q, and seasonal order I'll just keep it empty or use the default, which is 0, 0, 0, and fitted model equals model dot fit and print fitted model dot summary. Let's run this. You can see it just trained very quickly, unlike neural network like LSTM or transformers. So again, if you are an expert time series analysis, you can use this data to do further analysis and change the parameters if you need. Usually we just need to minimize the AIC. If you use auto ARIMA, means it will automatically find the parameters for you. In that case, it will try to reduce this AIC, and whichever parameters reducing the AIC the best, it will just give you those parameters. But I would suggest to use this method to find the parameters, because that will definitely give you better results compared to auto ARIMA. Like I'm just saying sometimes. Now let's do the forecasting. Forecast for next 2 years. We have a yearly data in terms of months, right? So I'm just forecasting like next 24 months. Forecast steps, which is 24. So I'll just have the heading as well. Model training. forecasting. Now forecast equals fitted model dot get forecast of steps equals forecast steps. Now it will just give you the forecasted values. After that you have to create the dates, right? Date with the months. You have to create that as well. Create the date range for the forecasted values. So forecast index equals pd dot date range start equals df dot index of -1, which is the last value in the training data, and periods equals forecast steps plus 1, and frequency, which is months, and 1 colon. So I'll also show why we need to use that 1 colon, and we also see what is there in the forecast variable. Let's run this. Now let's see forecast index. So you can see it also included the last of the training data. We don't need that. We just need the rest of the values. That's why we are using 1 plus. If we use 1 colon, mistakenly I mentioned it as 1 plus, we just have the 24 date time values. So let's do that here, and let's remove this and see what's inside the forecast variable. Remove one training date, or remove the start date. Remove start date. Okay, let's run this and run this forecast again. Forecast dot, you have like various values like confidence interval, predicted mean. So if you use predicted mean means it will just show you the values, like these are the prediction that was done. Let's make it a data frame out of this. So create a forecast data frame. So forecast df equals pd dot data frame of dictionary. We'll just mention the forecast. Forecast will be list of forecast dot predicted mean, which I just showed you now. Next, we can also display the confidence interval, like what is the maximum and minimum range that can happen. So lower confidence interval. This is also list of forecast dot confidence interval dot iloc. I'll just take the 0th index or dimension, and upper CI, again a list forecast dot confidence interval dot iloc of 1. So this will have the lower bound and this will have the upper bound. And after this, index equals forecast index, which we just created here. Now let's display the data frame. Function, okay, this is a function. Now you can see the date values, forecast, actual forecast, and lower bound and the upper bound. Let's plot it in the graph. Plot the forecast values to clearly see whether we got the right results. I don't think we will get, because we also need to do the seasonal parameters. So plot dot figure fixed size 12,6. Again, we just have to like do the same plot which we already did before. Plot df of passengers. I will have a label historical data and plot forecast df of forecast. Here I will have the label as forecast data and plot dot fill between. We just have to highlight the lower confidence interval and upper confidence interval, right? So for that we just need to use forecast df dot index, which is the dates. Only that area will be highlighted, and forecast df of lower confidence, lower CI, and again forecast df of. The auto suggestion is not working as expected, and color I will use K and alpha equals 0.1. Now let's define the rest like X label and Y label. X label will be date and Y label will be number of passengers dot title are passengers forecast, plot dot legend, which will display the labels, and plot dot show. Okay, I'm getting some errors. We got the graph. TZ must be string or TZ info subclass. So usually you will get this error when you are creating the new data like this. This date range is just causing some issue. So to resolve this, dot string f time of, I'll just have the year and month. Sometimes you just need to set the time zone as well. Let's run this and see whether it resolves the issue. Yes, it resolves the issue, but you can see the forecast is not very good. Let's also change the xticks, plot dot xticks rotation equals 90. Okay, still the dates are like not very clear, but the forecast is very bland. It's just having a median of all these things. So that's why we just have to do some additional parameters. I've just showed you because the influence of the parameters what we are choosing for the ARIMA model. Each parameter influences the model. Now let's get into the seasonal order. Seasonal order. So here initially I'll just have this capital Q, PQ, sorry, PI, PD and Q, and lastly we have the seasonal period. Oh, I think I made a mistake here as well. So seasonal period is 12, that is defined. We have to define the seasonal order now. Again we use this. So we are not going to do any additional differencing here. We can just use the same graph as it is. If you are using additional differencing for this means you can update the parameter if you are using additional seasonal differencing. So for now this will be 0 as we don't do any difference. Now we will check the PACF plot first. In the PACF plot for the seasonal order, we have to consider only the data points at the seasonal period. So seasonal periods are 12, 24, 36, etc. So here only 12 is outside of the confidence interval. So we just have only 1 point. So P will be 1. So after that we will see the ACF plot. In the ACF plot we can see around like 3 data points are outside the confidence interval, 12, 24 and 36. So I will set it as 3. Let's run this. Let's run the model again. You can see from the previous AIC it is very less. And let's do the forecast again. Now you can see how the values are drastically changed. You can clearly see the increasing trend and the values. I can definitely vouch for it. This forecast is pretty accurate, and I didn't use auto ARIMA or any other auto ML function. I just manually use this single graph and the previous graph to find the parameters manually. So you don't have to do all the brute force techniques here. You just have to understand the logic and specify the parameters correctly. Just because I introduced this seasonal order, it just makes a huge difference in the results. So that's pretty much it, guys. Like this you can predict for multiple years in the future. I can also change this if I want, but the forecast will be less accurate if you are moving too much into the future. If you have any queries regarding this video, please leave a comment below. I will definitely answer them. If you like this video, hit the like button and share it with your friends. See you guys in the next video.